All right, guys, in this video, we're going to talk about section 5.3, where we talk about more identities than what we've had. Specifically, we're going to focus a big portion of this on the sum and difference identities. And then we're also going to discuss the double angle identities. First thing I want to have you guys do is write down what these are, just like we did on the last section where we had our identities all nicely organized. We're going to do the same type of thing here. So for our identities, now I'm going to kind of take this one little section at a time because I did have to write kind of small, okay? But you're going to see both. This is a sum and a difference identity in one because their properties are so very similar that it is possible to write it as like one equation, but represent both in the same thing. Essentially, when you do cosine of something plus something, it does not break apart into be cosine of u plus the cosine of v. You can't break it apart that way as much as you'd like to. So it also doesn't it's not like cosine distributes, right? Like that's, sometimes people get that confused. This is not multiplying. This is cosine. It's its own little function. And when you evaluate this type of thing, if it's a sum, then what you're going to see here, you see how the minus and the plus, they're kind of switched. It's because if you're working with this sum in a cosine, then these values will be subtracted in the equation. If you're doing a difference, then the values are going to be added. And I know that sounds opposite what it should be, but it is the way that the cosine one works. Sine is a little bit more straightforward. It does line out to be the one that you want. But I want you to look very closely here with cosine. They couple cosine of u times cosine of v. They use the opposite sign of what you want it to be. And then it's sine of u, sine of v. So the cosines are grouped, the sines are grouped. And you use the opposite sign of what you think it should be. Now, sine, it does a little bit of a mixy-matchy. So if I do sine of u plus v, then this is sine u cosine v. So it kind of uses both sine and cosine in this first term. Then you're going to use the sign that you believe you should, right? So if you were adding, this is adding. If it was subtracting, subtract. And then you're going to switch. Before you had done sine of u, cosine of v, this is cosine of u, sine of v. So that pattern switches around. Okay, we're not going to go through the proof of these right now because it is a little extensive. So I have a feeling that very few of us would follow, but you can find the proof for sum and difference identities if you can search for it online. You can watch. I'm sure people have it posted. All right, tangent of u plus or minus v. Tangent's a little bit more complicated because tangent always is. He's got to be a little bit of a problem child here. But tangent of, you're going to have this be tangent of u, and then it's the sign that you think it should be. So if this had been a sum, you'd be adding. If this had been a difference, you'd subtract. Okay. Then tangent of v. So tangent of u plus or minus tangent of v all over 1, and then you're going to use the opposite sign, right? Minus plus tangent u times tangent of v, okay? So there's your sum and difference identities. We're going to practice using those in just a moment. Let's go ahead and get these double angle identities written down, okay? That's the category I'm on here right now, double angle. Okay, now this is one that we actually will be proving in just a few minutes. So some of these ones tend to be a little bit easier to prove once you have the sum and difference identities, and you'll see how that works in a few minutes. All right, but for the double angle identities, we've got sine of u, or sine of 2u. That's why it's called double angle. You double the angle, right? Sine of 2u equals 2 sine u cosine u. And this is, again, being multiplied, right? And then here, cosine 2u, you have 3 different options that you can work with, depending on what's going to benefit you the most. So you pick whatever you like best in your particular problem. And then, of course, tangent's a little bit more tricky, but at least we don't have the plus or minus thing with the double angles. I think the plus and minus thing can get a little bit tricky on the sum and difference ones. All right, with all that being said, these were the identities. We're going to move into the problems. Okay. So just like last time, I actually don't really have a lot of notes for you guys today. I know that's a little bit different. But these sections, really the only notes we're getting what those properties were. And then from there, it's just applying them. So that's what you're going to see here is we're going to apply them and just go through a few examples. Okay. The first one asks you to find the exact value of cosine of 15 degrees. Now, if you don't have a calculator, we have to be able to work this a different way than what we do with the just straight up unit circle, because 15 degrees is not a special angle on your unit circle. Okay. You also can't go look at 30 degrees and then cut that cosine in half. It doesn't work that way either. So anyways, we're gonna practice doing this a different way. All right, we're gonna actually use a sum or difference identity to do this, and we're gonna make it be cosine of special angles in order to solve this one. And you might be thinking, like, what on earth are you talking about? How on earth could we make this a special angle? I can't change the angle I'm working with. And you're right, we can't change the angle we're working with, but we can change the way that it's written. And that's called manipulating it. So look here, we're going to have cosine, and this is a 15 degrees again. That's going to be equal to, and I want you to look at this, we have special angles. We got 30, 45, 60, 90, all those different things, right? All those special angles. Okay, I want you to visualize, how could I get 15 degrees using two of those special angles? Well, you could do cosine of 45 minus 30. 45 is a special angle, 30 is a special angle. If you subtract them, it does equal 15. So I have not changed the value, I've only changed the way that it looks. But this causes me to have to use a different identity for cosine. That's where I go to my identities and I say, okay, we're doing the difference, right? So we're going to be picking the bottom sign when it comes to our formula. We should be doing cosine of the first thing times cosine of the second, then plus sine of the first thing times sine of the second, right? So we're going to have here cosine of 45 times cosine of 30. Again, it's the opposite sign from what we want it to be for cosine. It's a little weird. Plus, and we're going to do sine of 45 times sine of 30. And these are values we can figure out. Cosine of 45 degrees, if you look on your unit circle, it is square root 2 over 2. Cosine of 30 degrees, if you look on your unit circle, that's going to be square root 3 over 2. We're going to then be adding sine of 45 degrees, square root 2 over 2, times sine of 30 degrees, which is 1/2. Now, what's nice about this is we do end up really getting common denominators. If we multiply here, we get square root 6 over 4 plus root 2 over 4. And when you add these, you are able to just straight up add across the top because the bottoms do match. The one thing is that those roots do not combine into 1 because they don't have the same number underneath them. So we're going to say this is square root 3 plus square root 2 all over 4. And there's that answer. Sorry, that's a little bit squished on there, but that's what we're looking at. Okay, next one. All right, next one actually is asking us to prove, excuse me, this one's actually asking us to end up proving another idea. If you guys recall, this is the cofunction identity. I'm trying to find that so I can pull it back and show you. Here. This is asking you to basically prove the cofunction identity, okay, from our last graphic organizer. So we have the skills to do that now that we've talked about sum and difference. So let's see where that comes from or how we get it. Okay, so for me to prove this, it's actually not as many steps as you might think with it being a really big identity that we use. Get my paper set up here. We're going to start out, and I know we don't always like the idea of proving. It's just justifying why something works. And you do that all the time when you show work, guys. So if I say to prove this, then what we're going to do is we're going to say, start out with what we've got to begin with, sine of pi over 2 minus x. And then in order to prove this thing, think about how we can adjust this. Well, this is a difference inside the sign. So we can look here and look at how sine of a difference works. Again, you're going to use the bottom symbol because difference was the bottom one. But we're going to have sine of the first times cosine of the second minus cosine of the first times sine of the second. Okay, so this is going to look like we should have sine of pi over 2, then cosine of x minus, and then we're going to switch this around a little, do cosine of the first one, and then sine of the x. But this was just your sum and difference identity. Okay, so for proofs, we like to be able to justify why we did what we did. Okay, so just off to the side, I'm going to say this was, I'm just going to say, honestly, sum and difference identity, because I'm running out of space to write sum and difference. So plus or minus identity. Okay, now from there, we're going to take this and just take another line of work straight down and clean this up some. Okay, because sine of pi over 2, if you look at pi over 2 and look at the y value, that's going to give you 1. We don't know what cosine of x is, but we know it's going to get multiplied times 1. Then over here, you look at minus cosine of pi over 2 is 0. That's going to get multiplied times sine of x. And all we did there, as far as like your properties, we just really evaluated. So we just did, we evaluated sine and cosine. All right, next step, we're going to combine like terms and just simplify. Really, that's what we could have said on the last one, is also simplify. 1 times cosine x minus nothing is just cosine x. So all we did was simplify. And then boom, we're done. We got what we wanted to get. This is proven. So proofs don't have to be this long, drawn out, arduous thing. It can be fairly simple. Okay. Here's your example 3. All right. Now this one's a little weird. It's just working backwards, but it feels weird. So it may take us a second to kind of really grasp what's going on. They're wanting you to figure out what was the original problem. Basically, what were they doing sine and cosine wise before, and then you can clean it up a little bit. So they're saying that once they plugged values in to their sum or difference identity, that it turned into this. I'm going to work backwards. Okay, so I'm going to start out with that, and then we're going to simplify ourselves down. So I'm starting out with cosine pi over 3 cosine pi over 4 plus sine pi over 3 sine pi over 4. So the one I'm going to look for is the one that uses cosines in like together and then sines together. Also, that's separated with a plus sign. Okay, so looking at my sum and difference, as far as where I see that happening, cosine, right? This one had sine cosine. That's not what my problem's doing. My problem is using the cosine sum or difference. Also, because they're separated with a plus sign, that's that bottom symbol. That means that they actually were doing a difference. And we can tell what the first number was supposed to be for each thing because they put them in that proper order. Okay. Okay, so for me to figure out what this is actually going to be, we're going to look and say, okay, well, this was cosine of, and then we're going to have this first value, pi over 3. Remember, we agreed this was a difference, so minus pi over 4. And then we can clean that up. Now, you do have to get common denominators with these fractions. These do not have common denominators right now, but it is the easiest thing to get 12 on the bottom. So I can turn this into being cosine of, if I multiply top and bottom by 4, it would be 4 pi over 12 minus, and then over here, multiply top and bottom by 3. So 3 pi over, 12. 4 pi over 12 minus 3 pi over 12 gives me 1 pi over 12. That is what they're originally trying to solve for. Okay, and then they had so we're just working the problem backwards, essentially. All right, guys. Next one. Next one's going to use tangent of 15 degrees. That's what you're seeing here, tangent of 15 degrees. Now, we had done something with 15 degrees earlier, so you can probably guess that we're going to do something kind of similar. But this is with tangent. So we are going to do a similar idea where we're going to use, it's very much like example 1, except using tangent. So we're going to use the tangent function, and we're going to turn it into a difference. All right, so I've got this tangent of 15 degrees is equal to tangent of 45 degrees minus 30 degrees. And what we're going to do is try to plug this in to the sum and difference one. So this is a difference. So when I plug this into the tangent thing, I make sure that I'm using the bottom symbol for everything. Okay, so just follow along with how we're supposed to be plugging these things in. Let's see if I can get this to show while I'm plugging it in there. Okay, so we're going to do tangent in the numerator. We're going to do tangent of 45 degrees. We're going to use, again, since this is difference, we're going to use the bottom symbol, so minus tangent of 30 over 1, but use the bottom symbol, so plus tangent of 45 times tangent of 30. Okay? And then it's going to take us a few minutes to clean this up. But honestly, we've used the identity. We just need to clean it up a little bit. All right, let's plug the values in. Tangent of 45, you look on your unit circle, it's going to give you 1. Now, tangent of 30. Guys, for those of y'all who are still struggling with being able to evaluate the sine, cosine, tangent, you can always fall back on your special triangles. So even if you don't want to grab for your unit circle, and my unit circle currently is across the room. I didn't grab it before I started making the video. So here's another way you can do it if you forget, okay? If you think back to your special triangles, assuming I can draw, all right, this would have been the 30, 60. The smallest side was considered 1. The hypotenuse was 2, and the longer leg was square root of 3. Tangent of 30 is opposite over adjacent, 1 over the square root of 3. So when I do tangent of 30, I can just look at that. Opposite over adjacent, 1 over square root of 3. You don't always have to reference the unit circle, okay? And honestly, for tangent, a lot of times the special triangles are easier. Rather than trying to divide a fraction by a fraction, which is what it does when you do the unit circle. On here, opposite over adjacent usually just is a little bit easier. Okay, over here. 1 plus tangent of 45 is 1 times tangent of 30. Well, we already did tangent of 30, so we know that's 1 over square root of 3. Now we got to keep cleaning this up. We got fractions inside of fractions. It's not great. I am going to get common denominators here. I accidentally wrote a 1. Hold on, pause. Give me a second. I need to find a whiteout. Okay. So I am going to get common denominators here. I need to get the denominator to be square root of 3 so I can add these. Okay, so I'm going to turn this 1 into being square root 3 over square root 3. Then I can subtract that square root of 3 that was in the numerator. This will be divided by, I'm going to need to get square root 3 over square root 3 again, because we're adding 1 over square root of 3. Okay, next line. This is going to give you square root 3 minus 1 all over the square root of 3. That is being divided, right? I'm going to go ahead and write it this way just to save us a little paper and because we're going to do the keep change flip. This is being divided by this denominator, square root 3 plus 1 over square root of 3. And when you divide those fractions, you have to do the keep change flip thingy. It's not my favorite phrase, but it works. Okay, so I'm rewriting this guy, but we're changing to multiplying by the reciprocal. And then plus 1 like that. Okay, 3's cancel, but nothing else does. Don't fall into a trap. These square root 3's don't cancel. The 1's don't cancel. They do not have the same sign between them. But what we do have is square root 3 minus 1 over square root 3 plus 1. Okay, so technically this is an answer, but it's not rationalized. So we do rationalize by multiplying by our conjugate. Okay, so I'm going to say right here, just as a little side note, rationalize by multiplying by the conjugate. Okay, on top and bottom. Conjugate, remember, is this, and it's the conjugate of, the denominator. I should have added that part. It's a conjugate of the denominator. So the conjugate of the denominator is just the square root 3 minus 1 instead. You use a different symbol. And the beauty of multiplying by your conjugate is it does end up making it to where the square roots will cancel out on the bottom. This is a skill we did earlier on in the year. Okay, keep in mind, this stuff does FOIL when you multiply it all through. So square root 3 times square root 3 is 3. Square root 3 times negative 1 is negative square root of 3. Negative 1 times square root of 3, negative square root of 3. Negative 1 times a negative 1 is a positive 1. That is the numerator. On the denominator, we have square root 3 times square root 3 is 3. Square root 3 times negative 1 is negative square root of 3. 1 times square root 3 is a positive square root 3. And 1 times negative 1 is negative 1. Combine. So all of this is just algebra. 3 plus 1 is 4, minus 2 square roots of 3. All over 3 minus 1 is 2. Negative square root 3 plus square root 3, gone. Last thing you can do is divide this 2 into both of those terms. So really this is 2 minus the square root of 3 when it's all cleaned up. Gross, right? Okay, so that is us practicing our sum or difference identities. That is this video. In the next video, we are going to do just a couple of problems where we're working with the double angles so that you can see how that stuff applies. But that will be hopefully a little bit of a shorter video. Okay, stay tuned for that, and I'll see you in the next one. Bye.